Okay, last time I talked about the singular potential, which was a bulk energy depending on the Q tensor Q, which I derived from this Onsager functional. So just to remind the situation, we've got now a homogeneous liquid crystal, so there's no X dependence, and rho of P is the probability of finding a molecule with orientation P. And we're going to allow the probability to be asymmetric, and so that rho of P is not necessarily equal to rho of minus P, and that's to allow situations where you have polarized molecules and things like that. So this is the form of the functional. So this talk today is going to be completely self-contained, and it's just going to be about this functional. So remember, there's the entropy term, or minus the entropy term, so tau is a positive constant, and then we have this molecular interaction term with a kernel that depends on the dot product of two vectors. And so I'll just, as a matter of notation, call E of rho, or what I called E of rho before, the integral of rho log rho, and K of rho is the interaction term, and the kernel we'll assume is continuous. So that means that this term is going to be bounded because the integral of rho is 1, right? So the only trouble is really going to come from the other term. And so here are 4 kernels that I will consider. And the first is the Miyasabi kernel that we discussed last time, and that's what we used to get the singular potential. And then minus a positive constant times t, k of t, that's the so-called dipolar potential. And then you can add them together to get the coupled dipolar Miyasabi potential. And then you have plus kappa, the square root of 1 minus t squared. That's Onsager's potential. So in some sense, the Miyasabi potential could be thought of as some kind of Taylor expansion in this, but it's not very clear. Okay, so now the first thing which I touched on last time is how do we define what a critical point is? Because we have this constraint that rho is bigger equal to 0. So formally, just forgetting about that sort of problem for a moment, we could calculate the Euler-Lagrange equation. So that would mean that we'd have to take the derivative with respect to rho of this. So we get a tau into 1 plus log rho from the entropy term, and then here you get k star rho of p, where k star rho of p is what's called the spherical convolution. So it's an integral over the sphere of k of p dot q, rho of q dq. And now we have a constant there. That's because there's a constraint that the integral of rho is 1. So you have, if you like, a Lagrange multiplier, which will give you a constant there. So this formally is the equation, the Euler-Lagrange equation for p in the sphere, and so you can integrate it up, right? You write log rho is equal to the rest of it, and so rho of p is going to be the exponential of minus 1 over tau k star rho, and of course the integral of rho has got to be 1, which is going to determine what this constant is, and so you've got to divide by the integral of that. Okay, so formally that's the answer. Okay, except of course it's not really an answer, because it's saying that rho is equal to some function of rho. Right? But formally that should be the Euler-Lagrange equation. But we have this problem that possibly a critical point, whatever that means. We have the problem that rho is bigger equal to 0, and so you can't make a two-sided variation if rho was 0 somewhere. And there might be some meaningful critical points for which rho is 0. of course, here we see that rho is bounded away from 0, but I mean, from this formula, but we don't know that because we don't really know what, say, a critical point is. Now, from the formula, notice that if k is even in T, as it is for the Miyazawa potential, then you get from this that rho of P is rho of minus P, because in the formula you get a k of minus P dot Q, which of course is k of P dot Q. Okay, so for any critical point, rho. Okay. But the question is, how can you give a rigorous definition of a critical point that respects the unilateral constraint and doesn't assume extra regularity on rho other than the fact that I of rho is finite? So let's let P be the space of continuous probability measures on the sphere, so L1 functions, non-negative, integrating up to 1. And so this is the definition I'm going to use. We're going to say that a probability measure rho in P is a critical point if I of rho is finite, and if for some rho bigger, some sigma bigger than 0, this lim sup, so it's a lim sup of a difference quotient. So this is the sort of thing you would expect to get as a kind of, if you like, variational inequality. This lim sup is bigger than or equal to 0 as lambda goes to 0 for all rho prime with I of rho prime finite and rho prime sufficiently close to rho in L infinity, so such that the L infinity norm of rho prime minus rho is less than or equal to this sigma. Okay, so that's a well-defined quantity, as a well-defined expression, this lim sup. And so it's a question of what can we do. So if rho is an L infinity local minimizer, in other words, that there exists a sigma bigger than 0 such that I of rho prime is bigger than I of rho if rho prime is in P and the difference between rho and rho prime in L infinity is less than sigma, then rho will be a critical point because you'll have that this expression is bigger or equal to 0. So okay, so here's a theorem which tells you that you didn't have to worry about all this stuff anyway. So rho is a critical point of I if and only if it's continuous, bounded away from 0, and satisfies the Euler-Lagrange equation as previously written down, which I'll call dagger. So I thought I'd prove this. It's sort of a little bit interesting. Okay, so let's take a rho and a rho prime, which in L infinity the difference is less than or equal to sigma, and I of rho is finite, and I of rho prime is finite. And note that well, k of rho and k of rho prime are well defined because we remarked on that before, and finite. So that means since I of rho and I of rho prime are finite, the entropy terms are also finite. Okay. And also, if you take the difference quotient in the k term, well, this is essentially the calculation I mentioned before. So the limit as lambda goes to 0, there's no difficulty in carrying out this limit, in fact, and is equal to the k star rho of rho prime minus rho. Okay, now what about the E term? Well, so E of rho plus lambda rho prime minus E of rho over lambda, that's equal to this expression where eta is rho log rho. And since eta is convex, this difference quotient is non-decreasing in lambda. Okay, so that's a key point. And so if rho is a critical point, then if we given delta bigger than 0, by assumption the lim sup is bigger than 0, so there's going to be a a decreasing sequence lambda j such that the difference quotients are going to be bigger equal to minus delta. And this, we know what's going to happen to this term from up here. So it's a question of what happens to this term. And in particular, that means that these integrals are bounded below. But these are decreasing, and so by monotone convergence, you can pass to the limit, and delta is arbitrary, and so when you pass to the limit, you get that this integral over S2 is bigger equal to 0, and here we're saying that log of 0 is minus infinity, as it should be. Okay, so now what I'm going to try and show is that that rho is strictly positive almost everywhere. Right? Now it's not obvious because rho log rho is 0 when rho is 0. So in principle, it could be. So this is we do a particular variation to prove that. So we let S be the set of P where rho is less than 1 over 8 pi, and we write by absolute value of S its two-dimensional measure. So that's got obviously to be less than 4 pi, or less than or equal to less than 4 pi. Why did I say yes? But of course when I multiply this by 4 pi, I get a half, right? So it's strictly less. Okay. So and now for S sufficiently small, we take this variation. So on the set S, where it's less than 1 over 8 pi, we increase it by S. Okay. So if it's 0, that will increase it, and of course that will mean that rho log rho decreases, right? And then on the rest of it, you have to subtract off a multiple of S to make sure that this is the correct multiple, to make sure that the integral of rho prime is 1. Okay? And so then rho prime is a probability measure, and rho prime minus rho in L infinity is less than or equal to sigma. And so that means that, so let's go back. So all the terms are bounded except for this Tor log. Okay, so I'm going to calculate the derivative of this with respect to S, and what am I going to say? That's not quite right. It's S deduced at S log rho. So what have we done there actually? S log rho. Okay, so log of right. So So I have the log of rho rho prime is what is going on there? Oh, it's all multiplied by rho prime minus rho. That's what it is. So the rho prime minus rho is on S. It's equal to little s. Okay, and then so the only term that I have to worry about is this S log rho term. Okay, so so that means that the integral of S log rho is bounded below, and that implies that rho is strictly bigger than 0 almost everywhere. Okay, so this is the first remark. Okay, now. This is a trick that sometimes works. It works in one-dimensional elasticity, for example, as well as that's why I learned this trick. In principle, you have problems where rho is large and when rho is small. Okay, so what we're going to do is make a variation which only on the set S epsilon, where rho is between epsilon and 1 over epsilon. Okay, where we won't have any trouble in calculating the Euler-Lagrange equation, if you like. So then you take a U, which is in L infinity of this set, and whose integral over S epsilon is 0, and you define rho prime to be rho of P plus S U of P in the set S epsilon and rho of p outside it for mod S sufficiently small. So now you see that because the integral over S epsilon of u is 0, that means that the integral of rho prime is going to equal the integral of rho. Okay? And and you're going to be close to rho, and so you can calculate the Euler-Lagrange equation on that set S epsilon. So you get that the integral of S epsilon of tau into 1 plus log rho plus k star rho times u dp is 0. Okay? But u is anything whose integral over S epsilon is 0. Right? So that means that this expression is in S epsilon some constant that may depend on epsilon. But of course, as epsilon decreases, S epsilon gets bigger, so it can't depend on epsilon, right? And you know that, because from the previous argument, the rho of p is strictly bigger than 0 almost everywhere, right? So that means that you have that this holds for some constant c almost everywhere, okay, which is the Euler-Lagrange equation that we want. So now since k star, since the spherical convolution is continuous in P, that means that that rho has a continuous representative, because which is because you get that from integrating the equation, and it's bounded away from 0, because otherwise, well, that's because the log is not minus infinity. It's bounded away from minus infinity, and so the Euler-Lagrange equation holds. And the other direction is obvious. If rho is continuous and bounded away from 0, and if star dagger holds, then you just calculate this. There's no problem in calculating the difference quotient, and so rho is a critical point. Okay. So this is an interesting remark that suppose k is in W11 of minus 1, 1. Okay, so you take the continuous representative of that. Then, in fact, any critical point is C infinity on the sphere. Okay. So this is a generalized result of my former student, Michaela Vollmer, for the Onsager interaction. So remember, the Onsager interaction is square root of 1 minus t squared, so it's singular at t is equal to plus or minus 1, but it is in W11. So I just give a sketch of the proof. It's sort of interesting. So it's sort of exercise in using spherical convolutions apart from ordinary convolutions. So take a C1 function rho on the sphere. So a function rho is C1 on the sphere if and only if these derivatives are continuous on the sphere. So I should have said probably that a continuous rho is in C1 if these derivatives are continuous. So what are they? Well, you take the derivative at t equals 0 of f of Ri of t(p), and Ri of t is a rotation about the ith axis through the angle t. Right? So for example, R1 of t is this matrix. And here's a lemma which says that if H is continuous on the sphere, then xi of the spherical convolution is continuous on the sphere. And that if H is C1 on the sphere, then xi of the convolution is the convolution of xi. So that's the analog of the derivative of the mollifier is the mollifier of the derivative, right? But it's done on the sphere. So a rough proof of the lemma is the following. So we want to compute. This is what we want to compute. We want to compute this. So this is equal to what is k star rho? It's the integral of k of p dot q. So you're differentiating it with respect to well, first of all, with respect to its argument, so you're going to get k prime of p dot q, and then you're going to have to differentiate. You'll get a q out there, and then you've got to you take the derivative of this. You're going to get an ri dot of 0, and then you've got the h there. And so now xi of k star h of p, that's the derivative of this expression, which is the derivative. And now the trick is that you change variables on the sphere. You use ri of t q instead of q. Okay, that's a measure preserving transformation on the sphere. It's just a rotation. But then when you then you're going to get an ri of t p dot ri of tq, which is just p dot q. So you get k of p dot q, and you've managed to put the ri of t inside the h. So that's the sort of the analog, and then when you compute that, you will of course get the xi of h of q inside. So that's the rough proof of the lemma, and then from the lemma you use the equation to first of all show that the log of rho is in C1, and that implies, since rho is bounded away from 0, that rho is in C1, and then you bootstrap, and you get better and better information. Okay, now the main question I want to discuss is axial symmetry. Okay, so now a rho in P is axisymmetric if it's just a function of one direction. So a function of P dot E for some unit vector, and the function is going to take -1, 1 to R. So for example, in the dipolar case, this is automatic. So the dipolar case has kernel minus sigma t. So k star rho of P is equal to minus sigma the integral of, so t is a dummy for p dot q, so p dot q rho of p rho of q dq, which is minus sigma times p dot the integral of rho of q dot q, which we call m. Right? So the formula tells you that rho of p is this expression, which just depends on p dot m, right? So and alpha is this number sigma over tau. Okay, so in this case, rho is automatically axisymmetric. On the other hand, for the Meyer-Saupe interaction, this is not obvious at all. Okay, and it was first proved in two classical papers of Fatkulin and Slastikov and Yu, Zheng, and Zheng, essentially simultaneous, and in this paper by two other Wangs and Zhao and Forrest, they also gave a proof, and they characterized, in fact, all solutions as a function of the parameter kappa, which is the thing in the kernel. This is minus kappa t squared, and tau, which is, of course, Boltzmann constant times temperature, and thus describing the isotropic to nematic phase transformation. So the proofs, all these proofs of axial symmetry, I just didn't have the courage to go through them. They're terribly complicated with special functions and so on and so forth. So there was a program at the Newton Institute, and I somehow spent 2 months thinking of how to prove this. And eventually I found an interesting proof. And so I'll explain what the idea of the proof is in a bit, if there is an idea. Okay, so let's let m be the second moment. That's the usual thing, the integral of q tensor q times rho. And so now the integral over the sphere of minus tau inverse of kp dot q is this beta is kappa over tau, right? Times p dot q squared times rho of q dq, and rho of p is equal to this expression where z of rho is the exponential of beta times m of rho dot p P tensor P. So we have equations which, I mean, there are, again, it's an equation we have to solve for rho. And what do we have to prove about the solution? Well, if we write M in its spectral decomposition, so eigenvalues gamma I, remember the sum of them, they're all positive and the sum of them is equal to 1, and you decompose P in that eigenbasis, then if you look at those equations, what you have to solve is for the gamma I. I mean, go back to the equations. So we're looking at these equations. So I'm going to calculate the second moment. I'm going to calculate the integral of P tensor P times rho of P, right? And in the P tensor P, there are things like P1 times P2, and those integrals are going to be 0. So it's a question of what the integral of P1 squared rho of P is, for example. And so that's why you get say Pi squared times this exponential has got to be gamma I times Z. So Z is this partition function. So these are the equations you have to solve. So what you have to solve them for the gamma I, all right? And you want to show that the solution's axisymmetric, which means that you want the two of the gamma i's to be equal. That's what corresponds to axisymmetry. So what you've got to show is that there isn't a solution with the gamma I all different. All right, so here we are. We've got three equations. They're sort of explicit equations, but of course they involve these integrals. Right, and you have to show that there's no solution with the gamma i's different. Okay, so now, so the idea of this proof is, well, the idea of the proof is not to do it the way the other proofs did it, which is to use spherical polar coordinates, and so that gets you involved in special functions and everything, and it gets terribly complicated. But the thing is, if you choose spherical polar coordinates, you choose an axis, and that desymmetrizes the problem somehow and causes lots of confusion. So the idea is not to use spherical polar coordinates. So what else can you do if you're not going to use spherical polar coordinates? Well, the only thing that I could think of doing was to use some integral identity on the sphere. So here's a lemma. So this is the key to doing it. So if you have a smooth function of u of P on the sphere, then this integral is 0. The integral of the sphere of P, so this is, u is a function of P in R3, okay, so there's no doubt what these derivatives mean. So the integral of S2 of P1 du dP3 minus P3 du dP1 is 0. Well, apply the divergence theorem to this vector, du dP3 is 0 minus du dP1. Its divergence is 0, right? So therefore, using the divergence theorem, this vector dotted with the normal integrated over the sphere has got to be 0, but the normal is P. Okay? So that's where you get that this integral is 0. Okay? So here's the theorem. All critical points are axisymmetric. So suppose for contradiction that you've got a critical point with the gamma I all different. I'm going to apply the lemma with u is P1, P3 rho. Okay. So if we maybe try and look at that for a second and then go back to the, so my u is P1, P3 rho. So u is P1, P3 rho. So for example, when I take P1, P3, I'm going to get a P1 squared here, and then I'll have a rho, of course, and I'll get a P1 squared minus P3 squared here, and then I have there's a so U is P1, P3 rho. So I'm going to get a P1, P3 d rho dP3 minus P3, P1 d rho dP1, but I have the formula for how does that come? How does it work now? What is that? Yes. Hang on a second. Let's see what we're going to get. What we're trying to get. P times rho. Okay, that's right. So I'm calculating the rho d. I have to calculate d rho dP3, but you see the rho is given by the integral is given by the rho is given by what's the formula for rho? Here's rho, right? It's the exponential. So when I calculate, so I get terms when I'm calculating. M of rho is fixed, but I'm calculating the derivatives here. Okay, so and then I use the expression here, and that gives me the P1 squared, P3 squared rho. Okay, so we have this equation, and now, well, so it's actually, it's then we use the equation back here. Hang on. Oh no. I found a way to get rid of that. Let's see if, well, maybe I won't bother. It's not too bad. Okay, so now I've got to use the, no, let's haven't lost time to do that. Okay, let's see. It cured itself after a little, but let's see. Okay, here we go. All right, now we go back to the equation here. So now we're going to use this equation. So the P1 squared minus P2 squared is going to give me, so say P1 squared, if I subtract this for two different values of I will get a difference of gammas over here. So so that means that if we so on the left we'll have gamma 1 minus gamma 3. Gamma 1 is by hypothesis not equal to gamma 3, and so we'll get that that 2 beta times this integral is 1. Okay, because this is just gamma 1 minus gamma 3 times the integral of rho. Okay, so all right, so now you've got this expression, and so now similarly, as gamma 1 is not equal to gamma 2, you have the same thing where you replace 3 by 2, and then you can subtract those two equations, and then you get that the integral of so I've now substituted for rho, which is this exponential divided by z, and so this integral is 0. Okay. And now you interchange P2 and P3 as integration variables. Okay, so you're allowed to do that without changing, that's a measure preserving transformation. So, but then you have to swap P2 and P3 here, and P2 and P3 here, right? So then you get that this integral is 0, and then you add these two things together, okay, and then you get P1 squared into P3 squared minus P2 squared, you get this exponential, and then you get, it's multiplied by 1 minus this exponential of beta, gamma 3 minus gamma 2, P2 squared minus P3 squared. And that integral has got to be 0, and then you notice that when gamma 2 is not equal to gamma 3, that this integrand, actually this factor here, has a P3 squared minus P2 squared times this has a fixed sign. It's either strictly positive or strictly negative, but the integral is 0, which is a contradiction. Okay, so that's the proof, and it's much easier than the other proofs. Now, this is the picture that was proved by Fatkulin, which was given by Fatkulin and Slatnikov and Zhang and Lin, I think. And so this is a bifurcation picture for solutions according to the Maya-Saupe theory. So now we know that all the equilibria are axisymmetric, so they have to satisfy that 2 of the gamma i's are equal. So suppose the gamma 1 and gamma 2 is lambda plus a third, so the gamma 3 is a third minus 2 lambda. And I'm plotting lambda vertically against the temperature, which is tau over kappa, effectively tau over kappa. And so you see for large temperatures, the solution is lambda is equal to 0, which corresponds to the isotropic state rho of p is 1 over 4 pi. So 1 over 4 pi is the minimizer for tau sufficiently large up till this point, which tau over kappa is 2 over 15, and it's stable. So it's a local minimizer, and then you get bifurcation to a branch of nematics where 2 of the eigenvalues are equal, and this branch is stable from this point. Okay, so in fact, this is stable up until 2/15, and then it transfers to this one, and the other branches are unstable. So that's a picture of how the nematic phase bifurcates from the high temperature isotropic phase according to the Maya-Saupe theory. So in relation to the singular potential, which we did last time, remember that that's the formula for the Q tensor, of course, and we looked at this set script E, which was the set of Q's which are symmetric and trace free and with minimum eigenvalue bigger than minus a third, and the singular potential was the minimum of I of rho among rho in P with Q of rho is equal to rho, and we denoted by rho of Q, the rho sub Q, the unique minimizer. And then you can show that Q star is a critical point of the singular potential if and only if rho of Q star is a critical point of I. So that was proved by Jamie Taylor. And then that Q star is a local minimizer in E if and only if rho of Q star is an LP local minimizer. So a local. I mean, this is a local minimizer. This is of course a function of. It's just a function of a finite dimensional variable. So it's obvious it doesn't matter what norm you have. But if and only if rho of Q star is an LP local minimizer of I. Okay. So that's a kind of satisfactory connection between the critical points and the critical points of the singular potential. Now, for the coupled dipolar Maya-Saupe interaction, you can apply the same method, and in this case, critical points rho are solutions to this equation, where z is this exponential. So you have this extra term alpha m dot p. And so if you've got a critical point for the Meyer-Saupe interaction, then that will satisfy m is equal to 0, because m is the first moment, and thus it's going to be an axisymmetric critical point in the couple case. So that for the purpose of proving that rows satisfying this are axisymmetric, you can suppose, without loss of generality, that the first moment is not 0. Okay, and then you choose the eigenbasis of m, so that the third component, since m is not 0, you can choose the eigenbasis such that m dot e3, which I call m3, is strictly positive. And then these guys proved that in fact m1 and m2 are 0, so that means that the first moment is coaxial with an eigenvector of m. And also they proved that if rho is an L infinity local minimizer, then gamma 3 is bigger than the maximum of gamma 1, gamma 2, and rho is axisymmetric. Whereas in general, critical points need not be axisymmetric. And so using this integral identity method, you can prove a slight generalization that if this expression is positive, then gamma 1 is equal to gamma 2 in the selected coordinate system, so that rho is just a function of p3, and so it's axisymmetric. So really it's the same sort of argument, it's just a little bit more complicated. Well, now, what about non-axisymmetric critical points? So I'm going to give you a general criterion for the existence of non-axisymmetric critical points that applies in particular to the Onsager interaction, but not to the coupled Meyer-Saupe dipolar case. Now, to do this, I'll call it the cubic group. Consists of real 3x3 orthogonal matrices, with each row and each column having a single non-zero entry, plus or minus 1. So these are the orthogonal matrices that map a cube to itself. Okay, so you put the cube in standard position, and you see that the matrices that map the cube to itself have this form, and there's 48 of them. Okay, and now we say that a row in a probability measure row has cubic symmetry, provided that row of QIP is row of P for all I and almost every P. So we're going to try and prove the existence of some row that have cubic symmetry but are not axisymmetric. So we're going to let 1 over 4 pi be the isotropic distribution rho iso. So here's the theorem that there exists a non-axisymmetric critical point with cubic symmetry if this integral, the integral of the kernel times the 2rth Legendre polynomial dt is less than minus 2 tau for some r bigger than or equal to 2. Okay, so that's fairly mysterious, but so anyway, the proof uses the following proposition, that if you've got a row, a continuous row, which is axisymmetric with respect to two non-parallel axes, then rho is isotropic. Okay, so you can either do this by brute force, which is quite unpleasant actually, or there's a very nice result of Lowenthal, which says that any rotation is a product of a finite number. So you're given E and E bar, which are non-parallel, then any rotation is a product of a finite number of rotations about E and E bar. And so so that would mean that you take any rotation and okay, so it obviously follows from this remark. Okay, so we want it to be okay. So we're going to use this. Okay, now, so that means that if rho is continuous and it's axisymmetric and has cubic symmetry, then it is isotropic, because if you have cubic symmetry, then you are invariant to so wait a minute, here we go. Because it's a function of two orthogonal directions. Okay, so here's the proof of the theorem that you, or a sketch of it anyway. So there exists a minimizer among rho having cubic symmetry. Okay, that's essentially easy. I mean, the set of things having cubic symmetry is non-empty because the isotropic state has cubic symmetry, and so you just apply the direct method of the calculus of variations, and the cubic symmetry is preserved using, in weak convergence and so on. So then you have to show that this minimizer rho c is a critical point of I. So that's not obvious because you've got this constraint, but it's a sort of example of the principle of symmetric criticality of Palais. But it's easier to sort of do it directly. So that's the second step, and then you now, if R is bigger or equal to 2, there is a 2rth order spherical harmonic having cubic symmetry, and an example is given by the sum of the P2R of P1 plus P2R of P2 plus P2R of P3. So this is a spherical harmonic, and it has cubic symmetry because you can permute and change the signs of P1, P2, and P3. And now here's a very interesting theorem, the Funk-Hecker theorem, and it says that that any nth order spherical harmonic is an eigenfunction for any rotationally invariant operator. So the integral of k of p dot q times any spherical harmonic is given by, well, and then it tells you what the eigenvalue is. It's 2 pi lambda L, and lambda L is this expression that you saw in the theorem, the integral of k of t, p1 of t dt. So kl of lambda L is the integral of that with pl of t. So that's a very interesting result, and so now you can apply it with that particular spherical harmonic, and you get that the integral of k of p dot q times u is equal to 2 lambda R2R u of p, because it's a spherical harmonic. And therefore, now what you're going to show is, what you want to show is that the isotropic state is not the minimizer. Okay, so I'm going to calculate the second variation around the isotropic state, which is this derivative, second derivative at t equals 0, and then one term you get is from this calculation, which is the lambda 2r times this, and then you get the expression from the rest of the energy, and that tells you that if this is we're assuming that this expression is negative, and so the second variation is negative. So that means that this is not the rho c is not rho iso, and so by the corollary it's not axisymmetric. Okay. And now for the Onsager interaction. so you work out what the numbers are, and you find that there's a non-axisymmetric critical point with cubic symmetry, provided this expression holds. So this is the temperature is less than 2 to the minus 8 times pi kappa. Now, Vollmer studied the bifurcation from the various eigenvalues of the Euler-Lagrange equation linearized around the isotropic state. So now the special thing about the Meyer-Saupe interaction is that all the eigenvalues coincide. So there's essentially only one eigenvalue, but of infinite multiplicity. But usually you get infinitely many eigenvalues, and for the Onsager interaction you get these explicit expressions for the eigenvalues. And she showed that for tau is equal to 1, so that's the first bifurcation point, that the bifurcation was locally to axisymmetric critical points. Okay, so whereas for the Meyer-Saupe case we know that everything is axisymmetric, we at least know that from the first bifurcation point you bifurcate locally to axisymmetric critical points. So an open question is whether for the Onsager interaction local or global minimizers are axisymmetric. So a typical thing that happens in this kind of problem is that you can get a secondary bifurcation off the primary branch to some non-axisymmetric minimizer. So that's a possibility. So I asked Pingmeng Zhang, who has an army of people in Beijing who do computations on these things, whether he could put them onto this to the Onsager case. And so they confirmed they confirmed numerically that such a secondary bifurcation occurs off the primary branch, and that again, and their calculations support the conjectures that all local minimizers are axisymmetric, and then they had some more sort of precise conjecture that for some tau there's a critical point with prismatic dihedral symmetry. So that's the in spherical polars. This is this condition. So that would be something that would be interesting to prove. I mean, I think that one could in principle try to minimize the energy subject to something like this, right? And try and show that there's a minimizer subject to something like this, and then show it's not the isotropic state or something. But then you have to show that it wasn't cubic either, I suppose. Okay, so that's everything for today. So not tomorrow, Friday, I will talk about a little bit about smectics and thin films of smectics. So.
Okay, so we'll meet on Friday. So tomorrow he's giving a talk at IISc.
Yeah, so we'll be in the MIC auditorium very close to the math department, so starting at 4. Anybody who wants to attend, that's what we welcome. Just 24 minutes from the math department.
It's at 4.
Yeah,
It's a 4.